Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see thin-walled rectangular section beam subjected to torsion. Okay, so this is our lecture video, the video topic. So let's see. So for what is there, thin-walled rectangular section beam subjected to torsion. So here rectangular section is there. So for that we are finding that torsion is there. In previous video we had seen what? Without torsion, if we want suppose anywhere, then what we have to apply the load that as the shear center, means along the x-axis and along the y-axis, sx and sy. We had seen if we will apply along the shear center, then there is no torsion. But now if anywhere other than the shear center, if we will apply, then torsion will be there. Then how to find that torsion? So for that we will see in this video. So let's see, a closed section beam subjected to a torque T as shown in figure. So just see here. So this is the closed section. Here torque T is acting along the z axis. Okay. Does not, in the absence of an axial constraint, develop a direct stress system. So just see other word. A closed system subjected to a pure torque T as shown in figure 1 does not, in the absence of axial constraint, means in the absence of axial constraint is there, then what happen? It will develop a direct stress. It follows that equilibrium condition reduced to, means what? Whatever the condition is there, that is del q by del s equals to 0 and del q by del z equals to 0 respectively. So for shear stress and along this s and z, that will be equals to 0. These relationships may only be satisfied simultaneously by a constant value of q. So this relation will be satisfied what? For a constant value of q. Then only this relation is valid. We deduce therefore that the application of a pure torque to a closed section beam result in the development of a constant shear flow. So let's see, we deduce therefore that application of a pure torque, if only torque is there, to a closed section, then what happen? Result will be there, one constant shear flow will develop on the beam's wall. Okay, how that is there? So just see, that is in the figure 2, that shear flow distribution in a closed section beam subjected to torsion. So here torsion is there. So how the shear flow will be there, that you can see in this figure. Later we will discuss. In next slide we will see how that is there. Okay. So here, so see. However, the shear stress tau may vary around the cross section since we allow the wall thickness T to be a function of S. Why? T is the function of as the surface area that changes according to that T. So T is the function of S. The relationship between the applied torque and this constant shear flow is simply derived by considering the torsional equilibrium of the section shown in figure 2. So just in this figure 2, here this cross sectional, they have just considered that elemental part, and for this only this delta S we need to find. Okay, so here the torque produced by the shear flow acting on an element delta S. So on delta S, how much torque is there? So what? Torque equals to closed integral. Right, the beam wall is what? PQ delta S. So how much torque will produce? PQ delta S. Okay, so for that particular section, this section PQ into delta X. Why? What is torque? Torque formula is force into distance. Right? So here our distance is up to what area that is acting. So that is ds. For that small area we are finding, right? What is force? Stress into, what is stress by area. So what is stress? Force into area, right? So force equals to stress is force per unit area, right? So from here you can see the Q is required. So force in stress into area will be your force. So we can replace this as stress into area. What is the stress here? That is shear stress is Q, and what is area here? That is P. So that's why it's a Q, P, ds. That for elemental strength. Now for the overall, see the figure, this is a closed curve. Right, whatever the shape will be there, either it's a rectangle, a circle or anything. If it's a closed, then simply we can use this one, the closed integral of PQ ds. Now whatever the area is there, according to the figure we have to take the area. Now just see, or since q is constant and closed integral of p ds equals to ta. P is that boom area and ds. So that p ds will be equals to what? 2a. So overall t equals to 2, or you can simply write this as t equals to closed integral of, so just see, what is that? Q is constant, that already we had seen here. Okay, constant shear flow, right? So t equals to q is out of the integral, and then p dot ds. So this p dot ds is 2a, hence this t equals to q into 2a, that is t equals to just arranging 2a q. So now we have the torque. Okay, so now note that the origin O of the axis in figure 2 may be positioned in or outside the cross section of the beam, since the moment of actual shear flow whose resultant is the pure torque is the same about any point in the plane. So just see this O either in this figure inside or outside somewhere here also we can put. Why? The reason is, okay, outside the cross section of the beam, since moment of the internal shear flow, that whatever the internal shear flow will be there, that will be same, right, about any point in that particular plane. So that is that origin might be inside or outside, that won't affect the internal shear flow, that moment of internal shear flow. So that can be anywhere. Okay, so for an origin outside the cross section, the term P ds will involve the summation of positive and negative area. So P ds will be what? Total area, either it's a negative side or positive side. So if we will take this as outside in first quadrant, right, and origin here and this in this diagram, right, so all area will be what? Positive only. But now we are taking just this part. So this part is positive. Oh, right. So along the origin means in this part will be positive, this part will be negative, right? So overall sum of all the positive and negative area will be the total area only. That is here, summation of positive and negative areas. The sine of an area is determined by the sine of P, which itself is associated with the sign convention for torque as follows. So just see here how that area sign will be there based on the sign of P. For that, what convention is there? So see the convention. If the movement of the foot of P along the tangent at any point in the positive direction of S leads to an anti-clockwise rotation of P. So see once again, foot of P along the tangent at any point in the positive direction. So see the figure, foot of P, right? So this is so P. So foot of P any direction along this one, P about, okay, point in the positive direction of S leads to an anti-clockwise. So when this will move in this direction, right, positive direction, this is the positive direction. So in that case what happened? We are getting anti-clockwise, right? So that anti-clockwise is there, okay, of P about the origin of axis. Hence P is positive, means it's moving towards the positive, which is anti-clockwise, and we can say P is positive. The positive direction of S is in the positive direction of Q, which is anti-clockwise, corresponding to a positive torque. Means if just because of this one, if these two are there, then torque also will be positive. Okay. Thus, in figure 3, a generator OA, generator here means through which we can just draw any circle or generate anything, rotating about O, will initially sweep out a negative area since PA is negative. So just in figure 3, right here. Below this axis also is there. So this one O P or this PB is there. So once this will move, this will provide what? Negative area. Or just here OP. If this will go in this direction, then it will give a negative area. So hence negative PA will be there. Okay. So now this sign convention for sweep area. What is that? But at B. Okay. So here is B. However, PB is positive. So now in this direction, positive direction it's moving, so that area swept out by the generator has changed sign. So now whatever the generator is there, so what is our generator? OPA, right? So see here, generator OA. Okay, so this is our generator. This you can say O P. This line is generator. So through this only this area is generating. Okay. Generator has change sign. At the point where the tangent passes through O and P equals to 0. So at the point, just here, tangent passes through O. So where is O? Here. That tangent is just here. This is this tangent and this is the cross section. So tangent passes through O and P equals to 0. That time. Positive and negative areas cancel each other out as they overlap, so that as the generator moves completely around the section, starting and returning to A, say the resultant area is that enclosed by the profile of the beam. So now what happened? First it started from here at point A, then it starts moving. Okay, then again it becomes positive, then moving, and finally it's coming to A. So now it's making a closed loop. Once it's reached to return that, once it's returned back to A, the original position, then only we can say that the total area will be the resultant of enclosed y, whatever this, the whole thing is enclosed, that will be the total area, that or area swept. So this whole will be the area, or we can say the resultant area that is enclosed. So that must reach, or you can say come back again point O, right? So here it should start, that can go like any this, depending upon the generator, but that must come here only, that should end here only. Then this area swept, whatever this area is there, that will be the resultant area. Okay, so let's see once again this thing. This is just for theoretical things. Next video we will see about the numericals related to this one. That's why in this is one short video, so that you can see just concept of that one, and later this concept in next video we will use that one. Okay, so first see a closed beam subjected to a pure torque T as shown in figure. So what we are taking, there is no other things, only torque is acting on any system, whatever is there, right? Figure does not, in the absence of axial constraint, means there is no axial constraint, it can be in any direction, right? Means axial, or it should be in x direction, y direction, or z direction, or anything, right? That there is no constraint in axial direction. Okay, develop a direct stress system, is that because of that stress will be developed along those axes, and hence that is called that's a stress system. Okay, once we have the stress system, means stress in along all the directions along the axis, it follows that equilibrium condition, right? So when equilibrium condition is there, that time del q by del s along the surface, because right now we are considering only for origin, so del q by del s, that will be equals to 0, because there is no change in that one, and del q by del z, because along this z we are taking, so torque along xy axis, because along the z we are finding, because along the z we are rotating, so del q, that z axis also is not changing, so del q by del z also will be equals to 0. Okay, the next is the relationship may only be satisfied simultaneously by a constant value q. So this will satisfied only if we will consider that shear stress q is constant. We deduce therefore that the application of pure torque, means shear stress is constant here, and already in starting itself we had seen that pure torque is only we are considering. So hence, because of the pure torque on a closed section beam, what happened? A constant shear flow will be developed on the beam's wall. Okay, then after that what we had seen in this figure, this was that del area of this one, right? This is P. So what was the P D, that is this one? Okay, P delta S, and this Q, or you can say simply we had seen also what torque is force into perpendicular distance. So force into del S, right? Force is what? Stress into area, right? Stress is our Q and area is our, this is sweeping, so P, QP del S, sorry, del S. Next step what we have to do, just this is the closed one, means we can go for the closed integral. So closed integral of P Q del S, right? And already we had seen that P is constant, right? Constant shear the strength. So this constant shear the stress. So this we can take out. right? Sorry, Q is the CRST, not P. Q is the CRST. So Q we are taking out. Closed integral of what? What is left? P del S. And this closed integral of P del S will give you 2A. So Q into 2A. Therefore, torque will be equals to 2AQ. Clear? Okay. So next, however, the shear stress tau may vary around the cross section since we allow the wall thickness T. Just here again, T to be function of S, means along the S, T will also change. It's not necessary that T should be constant. That okay. So because of that, what happened? Applied torque as constant shear flow will be developed. That all in previous slide also we had seen. So simply derived considering the torsional equilibrium. Now what we have to do? Take the torsional equilibrium condition. What is shown in figure. So from there only we got T equals to closed integral of PQ ds, and hence P closed integral of P ds will be the total area of that one, that is 2A. Hence T is equals to 2AQ. Okay. Now next, in the same figure, if O is the origin, now explanation of this one. So that also the origin O of the axis in figure 2 may be positioned in and out of the cross section. So in this what we can see, this we can put outside also, like here is the origin and here is our this. Okay, so we can put outside also. But here one thing you have to remember, when you will consider the area, in this case all the parts of the area will be in positive because in positive quadrant it is. But in this figure, this part is in positive quadrant, this is in the negative quadrant, right? So the total area will be what? Sum of all the positive and negative area. It's not like that only we have to take positive area. Magnitude, it's not like that. Suppose this part you are getting 2 and this part you are getting minus 3 or 3. So you have to subtract. So 2 minus 3 minus 1 area. No. Area will be added. Just means that magnitude you have to add. Either it's in the negative direction or positive direction. So here negative area stands for the opposite, that is in negative side of the axis. So anyhow, you have to just consider the magnitude and you have to add the magnitude. That's all. It's not with the plus minus sign and you just subtract it. Same like plus 2 and in this side minus 3. So 2 plus and minus. So minus 1. No. 2 plus 3. 5 will be the total area. Okay. So for an origin outside the cross section, the term PDS will involve the summation of positive and negative area. Okay. The sign of area is determined by the sign of P. So whatever the sign of P is there, if P is positive, then that area will be positive. If P is negative, then area will be negative. So when the direction of S leads to anticlockwise rotation, means when anticlockwise rotation is there, that time P will be what? Positive. When it's the clockwise rotation of S will be there, then the P will be negative and hence negative area will be there. Okay. Next, in figure 3, a generator OA rotating about O. So just see in figure 3. Okay. So this is there. OA, this is there. Right. So just this is generator, right? That can be of any size and it's rotating and it's forming a closed curve. Okay. So rotating about O will initially sweep out a negative area since PA is negative. So just see in this figure. Right. So for this part, first OA is there, it's a start sweeping. So this is under the negative part of the axis, right? This is below the axis, negative part of that side. So first, this part will be negative. Once it will go along the positive side, then the area will be positive. So total area will be sum of positive and negative part. Okay, it's not only the positive, the total area, that resultant area will be sum of the positive and negative area. Okay, so now once reach to that OA, reach to OB, that becomes OB, right? However, PB is positive, so that area swept out by the generator has changed sign. So now at B, if it's a positive, then their sign will change because P is positive and hence the swept area also becomes positive. Okay, at the point where the tangent passes through O and P equals to 0. So where the tangent passes through O, right? That time that will be that P is 0. Positive and negative area cancel each other out as they developed so that the generator moves completely around the section starting and returning to it. So whatever the positive and negative is there, if you will just start, that will get cancelled out. Means overall, again we can say from where, if suppose here 2 is there, right? So from 0 you started and you gain by 2. Now again you lose by 2. So what is there? Again you reach to 0 only. So from where whatever your starting was there, finally you reached also the same if you subtract. So means started by A. So first negative area and then positive area. So negative area and positive area will get cancelled, and hence the overall will again reach to A only. Okay. So this is the end of video. For this concept again you can refer to the that Maxen book of 4th edition. Now in next video we will see the numerical related to this concept. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.